Let us move on to the information section where Table 1 and 2 are presented. Table 1 provides us with some of the more common metric base units, including distance, time, mass, volume, temperature, and the amount of substance. While I suspect that you have seen, if not all, most of the base units, please make sure you are familiar with all of them. In Table 2, we show the relationship of the metric prefixes, using the base unit of meter. The prefixes give us orders of magnitude. You also have these relationships on your formula sheet, which is found at the back of your course pack and linked in Moodle. Each of these are exact relationships, and each of these, in fact, represent a conversion factor. To highlight this, let's look at the example of 1 meter is equal to 1 times 10 to the 3 millimeters. This relationship can actually be thought of as two different conversion factors, depending on the kind of calculation you're trying to do. That is, are you trying to convert from meters to millimeters, or are you trying to convert millimeters to meters? The type of conversion you're trying to do will define which particular form of the conversion factor that you need to use. Note that we need to have these various prefixes for ranges of magnitude, especially in chemistry, because we deal with very large quantities, in particular in industry, and very tiny quantities, like distances on the order of picometers, that is 10 to the minus 12 meters, or time in femtoseconds, that is 10 to the minus 15 seconds. I will make use of this chart and consider further conversions as we look at exercises 1 and 2. For exercise 1A, I ask you to read the question, think about the required unit plan, and think about what conversions will be necessary. You may want to stop the video while you're doing this. This question asks for the mass of this diamond in units of grams when given the original quantity in carats. We will be converting from carats to grams. Fortunately, carats has an exact definition in relation to milligrams, so we can convert carats to milligrams and then milligrams to grams. This is a two-stage conversion. Because both of these conversions are exact relationships, the significant figures are determined by the given quantity, that is the 7.5, which has two sig figs. The calculation equation looks like this. The units of carats and milligram will both cancel, and the final answer in grams is the two significant figures. I very much encourage you to lay out your calculations as a single line of conversion, such as what you see here. This keeps you organized and minimizes errors. Let us consider the next exercise, 1B. Here we will convert 5.51 milliseconds to microseconds. I am presenting this as a two-stage conversion, but you might be able to think of a shorter way to do this problem. I have provided a chart on the right, which is an extrapolation of Table 2, where I have interchanged the base unit. Instead of using the base unit of meters, I'm using the base unit of seconds. I know that there is a relationship between milliseconds and seconds, and there is a relationship between microseconds to seconds. For the first conversion factor, I write the seconds in the numerator to convert milliseconds to seconds. For the second conversion, I write the microseconds in the numerator so as to arrive at a final answer in microseconds. The calculation equation looks like this. 5.51 milliseconds multiplied by the first conversion factor and then multiplied by the second conversion factor with a final answer to three significant figures. Some of you may have taken a different approach in this calculation. A more efficient approach focuses on the relationship of microseconds to milliseconds. Combining two conversion factors used previously makes a third conversion factor of 10 to the 6 microseconds per 10 to the 3 milliseconds, or 10 to the 3 microseconds per millisecond. The calculation using the more efficient approach provides, of course, the same final answer. This approach also allows us to reflect on the significance of the answers. Given that a microsecond is a smaller unit than a millisecond, we would expect the final answer to be a larger value, by a factor, of course, of 10 to the 3. We move on to exercise 2, which will be the last example discussed in this video. This is one of the more important exercises because it highlights the approach required when the units involve an exponent, like to the power of 2 or 3. We are asked to convert centimeters cubed to decimeters cubed. In order to derive an appropriate conversion factor, I have provided once again a version of table 2 on the right-hand side. Ultimately, we want to convert centimeters cubed to decimeters cubed, but on the right-hand side, there's only a relationship between decimeters and centimeters. Actually, the table shows the relationship of decimeters to meters, and then meters to centimeters. I'm hoping, however, that you see that the relationship is essentially for every 1 decimeter, there are 10 centimeters. But this is not the conversion factor required. We want these units to be cubed. So the idea is that we have to cube the whole conversion factor, like this. This results in 1 decimeter cubed being equal to 10 to the 3 centimeters cubed. We're now able to do the calculation. 1,000 centimeters cubed times this conversion factor equals 1 decimeter cubed. Note that these are exact relationships and the rules of significant figures do not apply.